matrix. So I know it's a Sunday and you guys aren't feeling up to this, but you know what? It's time to get learning, because tomorrow you guys write physical sciences, paper 2. So you know what that is, aka chemistry. So today you're with me for Meg's Crazy Sundays and you're here with TK. So have you been?
Well, I've been okay.
Just okay.
And I had to be here as well, just to make sure that our matrix, they're out there, go there and pass the paper, the second paper,
yes.
physical sciences.
Oh my gosh. So today we're just going through questions, right? Just a few questions.
Yes, we're just going to go through questions, doing some revision on organic chemistry. We're going to have something to do with rates of reaction. There is also a section on redox reactions, but only focusing on electroplating, and we will also do some equilibrium questions. So I know that so many of you like that part, because most of the time it gives you some challenges. So I am here to help you sort those challenges out. We will be looking at some of those questions here.
Awesome, TK. So guys, let me just tell you what's going on here at Mindset. Even though it's a Sunday, I know you guys are up and ready for today. So, you know, Samsung and Mindset have powered up together, and Samsung have sponsored us the Learn Extra Exam Revision Marathon Competition. And what they've sponsored us is fantastic tablets. As you can see, the next prize up for grabs is this Galaxy Note 10. So if you want to be one of the people to walk away with this device, I suggest you get looking at the race numbers, and let me just tell you about the competition. So what happens is you look now on the website that I'm going to post, you look on the notes for Physical Sciences Paper 2 Live, you'll see. Yeah, it's our show right now. You look at the race number at the bottom, and then I post another link. You register on that link, and the work's done. Then you could stand a chance to win one of these awesome, fantastic Samsung-sponsored prizes. And don't forget, I'll tell you more about Curio later, Matrix, because you could also win some awesome prizes then. So I'm finished talking because you guys need to revise, and I'll be here with you. Talk to me on facebook.com/Learn Extra or Twitter @Learn Extra. So TK, I think we should get started.
Thank you. Let's go straight into the questions of the day. The first question that I have here is based on organic chemistry, and it says here, the letters A to F in the table below represent 6 organic compounds. So we've got 6 organic compounds in here, A, B to F, all right? And then let's just have a look at the questions here. Question 1.1, it says, write down the letter or letters that represent each of the following. So 1.1, an alkyne, okay? Now, when you talk of an alkyne, you would know that when we're talking alkynes, we're talking about unsaturated hydrocarbons. And these unsaturated hydrocarbons are the hydrocarbons where you will find a triple bond between carbon atoms, okay? So this would mean, if we go back there, any structural form that could be this alkyne that they're looking for would have a triple bond between carbon atoms. Or if we don't have a structure there, we will then have a name that will end with an "ene", E-N-E at the end. Now let's go back to the table and see which one is that, okay? Now, quickly, long before I even look at the others, the names and everything else, when I look at the structures, I can identify that one there, that I've got triple bonds between carbon atoms, the first 2 carbon atoms, and that will makes it an alkene. So this one is an alkene because of that triple bonds between carbon atoms. So my answer to 1.1.1 will be what? Will be A. So A is the answer there. Do we have any other one? Because possibilities are there could be more. When I look at the rest, I don't find triple bonds between carbon atoms. And even with this name here, it has got nothing to do with "ene", nothing to do with an alkyne. And therefore, A is the only alkyne that I have. So I would have to have that as an alkyne. So I've been referring to "ene" a lot. "Ine" there at the end to say we've got triple bonds. So there is nothing else here that talks "ine." Only even here, this is an alkyne. All right, because we've got triple bonds there. Alkene, remember, it's also unsaturated organic molecules, but those would have double bonds between carbon atoms. So not 3. We will be talking about alkenes there. All right, good. Next, 1.1.2. 2 compounds that are structurally isomers or structural isomers. In other words, when you write their structures down, they are not the same structurally, but molecular formulas are the same. In other words, they will have equal numbers of carbons, equal numbers of hydrogens around them, or equal numbers of oxygens if they include those. Now let's have a look. If I look at this table here, I can then, there are 2, 3, 4 that would have oxygen with. So maybe my isomers would be there. And then here I've got 2 that have got nothing to do with oxygen. Huh? All right, that's it. So, but then these ones would have, this will be an alkene, that one will be an alkyne, and therefore I can't really have much of isomers here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But because there is double bond here and there's a triple bond there, I cannot have them as isomers. In other words, they cannot have the same molecular formula and different structures. Now, these ones with oxygen, I've got E here. Let me just look at E. With E here, I've got that. Okay, and how many carbon atoms? 1, 2, 3, 4. So, and 5 down there. Now, this one is pentanoic acid. It will also have 5 carbon atoms. Allow me to write them like that, and allow me to do this. Here, this is the functional group of carboxylic acids there. So you know that there shall be hydrogens all over there. All right? Now, if I look at these 2, D and E, I have 1 oxygen here. I've got 2 oxygens there. So D and E cannot be isomers. Now let me look at D and F. D and F, because I am also eliminating B here. Why? Because B only also has 1 oxygen there. B and E, perhaps they could be isomers, but let's see if we can eliminate any of them or both of them as isomers. This is 1, 2, 3, 4, 5 carbon atoms. Yes, that could be possible. And then this is O, double oxygen O. I mean double bond O from the carbon to hydrogen there. Let's see, 1 oxygen. How many hydrogens? I've got 3, 5, 7, 8, 11, 12. Do I have 12 here? I've got 3, 4, 7, 9, 10. It's out. They can't be isomers. So what am I left with? I've eliminated all this. I'm left with D and F. Let's check them. With D and F, they have 2 oxygens. There they are. I have to look for number of carbon atoms. 1, 2, 3, 4, 5. Yes, we're still together up to this point. Number of hydrogen atoms, I've got 3, 5, 7, 10. Let me check here. This is 1, 3, 5, 7, 10. Now, these 2 here are isomers. So this one here, pentanoic acid, and the one down here on F, all right? Which we'll get to know not so long. These are isomers. Now, this is how I found out, okay? So the answer to 1.1.2, it will be D and F are isomers, okay? So 1.1.2, D and F. These are your structural isomers. The molecular formulas would be the same, but the structures won't be the same. That is the definition of what isomers are. Okay, now if you come here, for example, if you look at pentanoic acid, we have seen that it is how many carbon atoms? 4. Okay. 4 carbon atoms. How many H's? We counted them to be 10. And how many oxygens? We have them to be 2. Both D and F would have that particular type of molecular formula, but their structures won't be the same, as you can see here. All right, moving on. 1.1.3, a compound containing a carboxyl group. Now, a compound containing a carboxyl group must be a carboxylic acid. Okay, it must be a carboxylic acid. All right, so carboxylic acid, wow, why is it writing like this today? Am I too fast? Okay, so carboxylic acid, which molecule here do we have as a carboxylic acid? You are told basically, here it is, pentanoic acid. So D is your carboxylic acid. Okay, so D for that answer there. 1.1.4, an aldehyde. Now with aldehydes, I need to look at if it's a structural formula at the end, okay, I need to have this. Okay, at the end, I need to have a CHO. All right, so what I would have, in fact, I wouldn't have that, so I would have it in this way. So I will have something like that. Okay, so these here will tell me I'm talking about an aldehyde, CHO. If it's a molecular formula, I would get a CHO written like that at the end, okay? Connected to something else, of course, this side. So if I have something like that, I would say I'm talking aldehyde. If it is in the written form, okay, I must have al at the end. Okay, things like methanol, okay, propanol. So if I have that, I know I'm talking aldehyde. Let's go back to the table. You come back to the table, what do you have? If I look at all this in terms of the written ones, there's nothing that says al at the end, so I won't look at what is written. Structural formulas, if I look at those ones, this is not CHO, there's 2 O's there, it won't help me. There must be only 1 O. This one with only 1 O is an alcohol, it's an OH. It's not, okay, it's not an aldehyde, so I can't go there. This is pentanoic acid, it's a carboxylic acid. I'm not going to go there. So which one will have just 1 oxygen, and at the end, it's this one here. So substance or organic molecule number E is the aldehyde. So E is the aldehyde. The one that is an alcohol, I have already mentioned that as we were looking for our, our aldehyde here. Look at it. It's this one here where you have the OH. I've just written a lot on this table here, but I think you can still see that OH there. So that is organic molecule number B. So you will come here and say the one that is an alcohol is number B. Okay, so that's how you were supposed to look at that one. Let's move on and let's see what is next on this question. Okay, now coming to 1.2, it says write down the IUPAC name of compound C. Now, if you go back to compound C, you look at it, you've got 1, 2, 3, 4 carbon atoms on your long chain. This will be the long chain. So let me identify my long chain. Remember, when you do your IUPAC naming, identify your longest chain. The next thing, you identify your functional group. And of course, functional group along your longest chain. So there is your functional group. We are talking about an alkene here, an organic substance where you've got double bonds between carbon atoms, okay? So what will be the name here? This one becomes carbon number 1, that is carbon number 2, carbon number 3, and that is carbon number 4. On carbon number 2, I have that. We call it the methyl group. Okay? So if I want to name it, 4 means I'm talking butene because it's an unsaturated alkene. It's an alkene. So I would say, okay, I've got 2 methyl here. I've got a methyl group on carbon number 2. So this is 2 methyl. And it's a butene. But what makes it a butene is the double bond way on carbon number 1. So there is from carbon number 1 to carbon number 2, we have got that double bond here. So it will be 2-methyl but 1 in. Okay, so that's how you would name it. I think it will be time for us to have some breather, and then we move on.
Already, I think we need to take a glass of water, and that's exactly what you need to do. But send through your questions during the ad break. It's facebook.com/learnextra. And TK and I'll have a look at any questions you want us to look at. So we'll see you after the break. Welcome back, Matrix. So, as we all have spoken about and as we all know, you guys are writing Physical Sciences paper 2 tomorrow. So, what's been going on? What are the questions? I do have the questions here, so let me just try find them for TK. Oh, but first, let me just tell you about Curio. Curio, guys, is something that you answer questions as quick as you can, and hopefully as correct as you can, or the most correct. And then you, Matrix, it's only for you. It's a competition that we've established just for you. Could win either 100 Rand airtime if you're the learner who gets the quickest answer and the most correct answers, or you go into another draw to win a S3 Mini. So that's the big competition. So the more you do, you get to go into that competition and win a S3 Mini. But don't worry, we're about to post where you click and how to register on Curio for you guys. And the link or the key password you type in is PS12. Physical Sciences, grade 12, obviously. So let me just find you your questions, TK. Now I just need to find these people. Just need, really? Sorry guys, sorry. Just need to find these learners' questions for you.
Let me just do this whilst you're trying to find one of them.
Thank you.
And we have now given a name to compound C. And we say compound C is 2-methyl. I hope you have seen that. You've found out or you've understood how the naming came about. So that is 2-methyl but 1 in. In because of the double bonds between the carbon atoms. So this is an unsaturated hydrocarbon. It's an alkene. All right. So coming to the next one here, 1.2.2, the structural formula of D. Now, what is D? If you go back to D here, let's just have a look at D. It says pentanoic acid. So this is a carboxylic acid, pentanoic acid. I need to have 5 carbon atoms. So 1, 2, 3, 4, 5. There I am. And at the end, I need to show this functional group of the carboxylic acid. the COOH. I think you can see that. And then now I need to just put in all the hydrogen atoms that should be there as well. Remember, if you just draw these lines without the hydrogen atoms, they mean nothing. They only mean a bond. And a bond to what? Because a bond is a bond to something. All right.
You ready?
Yeah.
Sorry, I
there's some
delayed you
questions.
guys.
Yeah.
Apologies. But
Okay.
now, okay. So, Tumonza says, please help. When do you substitute, eliminate, and add to reaction?
Okay, so I suppose the question is about when do I have an addition reaction? When
Yeah,
do I have
I
a
think it's
substitution reaction? When do I have an
like that.
elimination reaction? One, basic things that you need to understand, and we're going to have one question that will try and help us here. One, if you have got alkanes, alkanes are saturated hydrocarbons, okay? These ones do not have double bonds between carbon atoms. Saturated means they can't take anything more. It's like having a full taxi, all right? A minibus. It is taking off. There should be no more passengers coming in. We would say it is saturated. Those are alkanes, all right? Things like butane, propane, methane, ethane, all right? Those ones. So because they are saturated, they can only undergo substitution reaction. For you to have them to react, you need to remove something that they have and replace it with something else. So those are the ones that will undergo substitution reaction. We will continue with this later on in another question. But if I have got unsaturated hydrocarbons, the alkenes and the alkynes, where you have got double bonds between carbon atoms or triple bonds between carbon atoms, there you have got spaces that you can still unlock and use. You can put more things there. Those are unsaturated, and therefore addition reaction can happen. You can add things more into these molecules. So that's where addition happens. Now, elimination. With elimination, you need to create conditions for elimination to happen. You can do elimination with alkanes or haloalkanes, where you take what they have and remove it completely from them. You're not adding anything. You just remove what they have and you're forming a new molecule. And normally with elimination, once you have eliminated something, you are either going to end up with an alkene or an alkyne, depending on where you're coming from, okay? So you eliminate, so the carbon atoms now, they've got extra bonds between them that they can use for other reactions. So that is the basics, if you like, basic things that you need to understand. Let's see if we can apply it later on in another question. Is there another one quickly?
There's one more. They said, Shimunani, I hope I said that right. Can you ask TK if we can have an isomer on the compound that has different function groups, please?
Okay, I'm not so sure if you're referring to something like this. Earlier on, we looked at this isomers here, okay? We looked at pentanoic acid and this one here, which is actually an ester. This molecule here is an ester, and this, if you like, if you name it, you look at this part here, you can see this is a methyl group, okay? An ethyl group, all right? So this will be ethyl propanoate, okay? This is the O8 part. So this will be your O8 part, and this is your ethyl part coming from the alcohol, the ethanol. We'll explain it again later on. Now, this is ethyl propanoate. That is pentanoic acid. The structural formulas are different. The functional groups are different. Look at the functional group of your ester, okay? It has that there. It doesn't have the OH here, whilst this one has got the OH there. So one is a carboxylic acid, the other is an ester, but they can be isomers. Molecules may not only be isomers from the same functional group, no, but you can get isomers belonging to different functional groups, like we have had here. I hope that does answer your question. Let's just move on and answer more of the questions that we have here. All right. So coming to this one here, 1.3, we are told that compound F is prepared in the lab. Now, what is compound F? This is compound F. You can prepare it in the laboratory. Right? First question, how can one quickly establish whether compound F is indeed being formed when you are there in the laboratory and actually forming it, producing it? Okay? Now, compound F, I have said, this is an ester. Now, what is the common properties of esters? Is that they give pleasant smells or pleasant odor. Okay? And if an ester is being formed, if compound F is being formed in the lab, we will then feel, we will smell this aroma, okay? So we would say that there shall be a pleasant smell in the lab, pleasant odor in the lab. That will quickly tell us that that ester is being formed, okay? Next, write down the IUPAC name of the alcohol needed to prepare compound F. Now, let's not lose focus. Compound F is an ester, okay? Now, with esters, people understand this. There's a general formula for it, okay? If I have an alcohol and I make it to react with a carboxylic acid, okay, the product that will be formed will be an ester plus water. Okay? So if this is our general equation, and in this case, the ester that we have formed is this one. It's compound number F. And let's just give it a name already. Like I said, this part here comes from the alcohol. And that part here is an ethyl group. So this will be ethyl. And how many carbon atoms do I have there? I've got 3. So this will be ethyl propanoate. Okay? Now, the ethyl part, the alkyl part, is the part that comes from the alcohol. So if this alkyl part is the ethyl, it would mean that the alcohol that was needed to prepare compound F is ethanol. And of course, you can continue and try to find out what carboxylic acid was used. Obviously, it was propanoic acid. Okay? Propanoic acid. So that you can produce ethyl propanoate plus water. Okay? So there is the water molecule. And with ethyl propanoate, we'll be able to show you, I will show you later on, because this 1.3.3 here wants us to, okay, we're going to name it, and then as we have done, and I will also show you the structure there. Or the structure is there already anyway. So the IUPAC name, I've given it already. It's what? It is ethyl propanoate. That is the name of the ester, compound F, that we're talking about here. All right, that takes us to question number 2. And in question number 2, we're still continuing talking about organic chemistry, and it will talk to you about types of reactions. And I hope the one that spoke about, questioned about types of reactions, you are watching. So let's see from this question here. The flow diagram below shows how 3 organic compounds, okay, can be prepared from 2-bromo-3-methyl butane. So this is methyl butane, so we're talking about an alkane, okay? But then it has got that part there, bromo. These are special type of elements, group 7 elements. We call them halogens, okay? So that is bromine there. That's why they have bromo there. So group 7 elements called halogens. And because of that, we say that a substance like 2-bromo-3-methylbutane is called a haloalkane. We call it a haloalkane. All right? Good. Moving on. Write down the homologous series to which 2-bromo-3-methylbutane belongs. It belongs to haloalkanes. This is the homologous series to where it belongs. 2.1.2, structural formula of 2-bromo-3-methylbutane. Now, people, everything is there for you to really do it. It's given to you. You just follow the name and put what is relevant to those carbon atoms there. Because the first thing you need to number them, know from where left to right or whatever. And then also to know your main, the root name. The root name here is butane. So it means I would start by looking at how many carbon atoms do I have on butane. I've got 4. Okay, so that is just one bond there. Just get rid of it. Doesn't look nice there. Right, so that is my butane, all right, the root. Where do I have the bromo? On carbon number 2. So I will say carbon number 2. There is Br. Where do I have the methyl? Carbon number 3. So I would actually name or number my carbon atoms like this. Let me call this one 1. This is 2. That is 3. And that is 4. So on carbon number 3, all right, on carbon number 3, I've got my methyl group, 3-methylbutane. Methyl, that's what I have there. Okay, so that's a methyl. All right, and then when I'm done with this, this is 2-bromo-3-methylbutane. Then I have everything sorted out. I will then put the other hydrogens around here. There should be one more there, and then I will have the others there. So this is 2-bromo, okay, 3-methylbutane. The methyl part is that part there. All right, I've just moved it down there. But that's what you have. And then, of course, it mustn't take away our hydrogen there. That is the structural formula of that molecule. 2.2. Reaction 2 takes place in the presence of dilute sodium hydroxide. Now, this is a condition. If you're saying dilute sodium hydroxide, you've created that condition. When we deal with dilute sodium hydroxide involving haloalkanes, what we are going to see happening here will be substitution reaction. So I'm expecting a substitution reaction because of the condition that I am told here, dilute sodium hydroxide. Okay? So name the type of reaction which takes place here. It will be substitution. Okay? And because it's sodium hydroxide that is coming in here, I know that that substitution will be between the Br and the OH group. And because this OH group has got a special name, I can say that this is, once you separate the OH from something and place it somewhere, we call it hydrolysis. Okay? So I can say this substitution reaction, it's actually hydrolysis. But if you say substitution, that is good enough, you get your mark, you earn your mark. All right. Next, 2.2.2, structural formula of compound B. Now, you look at compound B. This is when reaction 2 has happened, compound B. Now, reaction 2 is the one that occurs with our haloalkane when you're having dilute sodium hydroxide. So the reaction, like I said, the substitution happens between Br and the OH. So what do you have? It means what you would have here is this. Where Br was, you have your OH, all right? And then you still have this side here. Mustn't forget, all right? So that's the H, I think, yes. That's the H. And then on 3, I still have the methyl, remember? So that is the methyl group. And then I have the last carbon atom there. Okay. All right, so the Br is now gone. And where has the Br gone? Remember, you are having dilute sodium hydroxide. This part here has been taken to come down there, and therefore whatever is to happen there ends up with the OH part taken by the Br. So that is basically what is happening there. Okay, although the question didn't want you really to go that way. Okay, but just explaining it. Down here it says reaction 1 takes place in the presence of concentrated sodium hydroxide. Write down the following. Another reaction condition needed for this reaction. If you bring in concentrated sodium hydroxide, you are aiming at elimination. And for elimination to happen as well, you also need to bring heat onto that reaction. So you need to heat the reaction vessel strongly to be able to achieve your purpose. So it is reaction 1. It's this one. You're from there and you're going that way. All right. Now, write the name of the reaction which takes place here. Okay? Write the name of the reaction that takes place here. We have said that when you do that, you're going to have an elimination reaction taking place. So you're going to say, okay, this one will be elimination. Okay? So you're going to have elimination there. And down here, the structural formula of compound A, the major product formed. So compound A here, once that elimination has taken place, what will be compound A here? And where is the elimination taking place? All right? I want you to look at this one here. Let's take it from here. That elimination that will take place will happen in this way. This Br is going to go with another hydrogen. But the question is, which hydrogen will it be? It will be this one. It will always be the hydrogen where there is a least number of hydrogen atoms around that carbon atom. It can't be this one. All right. That's something called Markovnikov's rule, and you need to, you don't have to know how the rule is stated, just understand how it is used. So what will be the product? The product will be such that this bond here will go, and then when these two are gone, you're going to have a double bond. Oh, sorry, there. You're going to have a double bond between these ones here. Okay? So at the end, your structure, oh, what is happening here? I think we can just stop here, and don't know why it doesn't want to stop there. Okay, there it is. So you're going to have this at the end, then double bond there. Remember here, it's your methyl group. Okay, so you're going to have that. Double bond there. You have your hydrogen there, and this B there is gone, and that hydrogen there is gone, so you are left with that. So you have moved, if you like, to an alkene and an unsaturated hydrocarbon. This is methyl butane. All right. I think we should have some breather as well now. And we will
jump back
continue
into it.
later on.
Okay, TK. So
Okay.
we're going to take a break, guys. I just want to say, Clive Kleinfeld, you wrote us on our page. He said I must holler at him and his friends for watching and studying now for chemistry tomorrow. And the race number, guys, is A0412. I'll try post it on the page and I'll try get it up for you. But for now, let's take a break. Welcome back, guys. So I know you took a quick little break and TK and I were talking about all these questions, but you know what? We are going to answer them for you. We're trying as fast as you can, and we can see that you guys really, really want KC. Is it equilibrium questions? Am I right?
Yes, it's an equilibrium question, and it is coming. We're going to look at one now.
Yeah.
Let's just finish off here, and from here we're going to look at some question that has to do with rates of reaction. Let's just close this one. Reaction 3 takes place when compound B is heated in the presence of concentrated sulfuric acid. Okay, write down the IUPAC name of the major product formed. Now, if you talk of sulfuric acid, there's one very special property of sulfuric acid. It has got a dehydrating effect. In other words, in whatever you put it on, it will take out the water. Okay, and if you remember very well, compound B basically was an alcohol. It was when we substituted the Br by the OH. So the hydrogen is going to go there. No, and the OH is going to go now. Let's just quickly look at that. You had this as a product for compound B. All right, this is what we had. We had this. Where Br was, we had the OH. Okay, so we had that. And then we would have that again. All right. So what happens is that there is the hydrogen, because that hydrogen is very special here. I need to have to look at it. Again, applying Markovnikov's rule, one hydrogen is going to go. It can't be any hydrogen there. It can't be any hydrogen here. It can be a hydrogen only where the carbon atom has the least number of hydrogen atoms around it, and that will be this one. So that is going to go. What is going to happen when that happens? When this is gone, it has been dehydrated. These two here, I mean, this open spaces here, would form a double bond there. And what will this be? You can actually name it from right to left. Your methyl group is there. Your bond, your double bond is here. If you start from left to right, it's on carbon 2. Right to left, it's on carbon 2. But then that becomes or takes precedence because it has got a methyl group there. So we'll say 1, 2, 3, 4. All right. Now, what will be this name here? It has now become an alkene. There is a double bond now that this is gone. So this is gone here. All right. Then we have a double bond there. So this is going to be what? It's going to be 2-methyl but. Where is the in? On 2 now. Look at how you have changed it. It was 3-methyl but 1 in earlier on. Now, look at where it is now. 2-methyl but 2 in. That's what has happened there. All right. Moving on, we need to look at this question here. Question number 3 talks to rates of reaction. It says calcium carbonate, okay, or calcium carbonate chips are added to an excess, now this is a key word, excess dilute hydrochloric acid, all right, in a flask placed on a balance as illustrated below. The cotton wool plug in the mouth of the flask prevents spillage of the content so reactions, reactants, and products, but simultaneously allows the gas that has been formed to escape. All right. The balanced equation for that is what you're having down here. All right. Right. Now, I said the word excess is key there. In other words, everything about calcium carbonate is going to react. It's going to be eaten away. It's going to go because we've got enough acid to react with it. At the end, we will remain with some acid because we've got an excess of that. All right. So all the calcium carbonate is going to go. There is the chemical reaction that happens there. Right. 3.1. Write down the name of the gas that escapes through the cotton wool plug while the reaction takes place. If you look at this, now, the gas is bound to be part of the product. It must be that thing that is being formed when this reaction happens. If you look at everything here, the only gas that is there is carbon dioxide. So basically, this was a giveaway question for you to just say part of the product there is a gas called carbon dioxide. That is the gas that is allowed to escape into the atmosphere. All right. Next. 3.2. The loss in mass of the flask and its contents is recorded in the intervals of 2 minutes. So every 2 minutes, they check how much mass has been lost. And that led to the graph that is shown below. All right? And then from the graph, write down the following. 3.2.1, the coordinates of the point that represents results that were measured incorrectly. Now, if you look at this graph here, there is a part of the graph. Oh, let me just use that color there. There is this part of the graph here. Obviously, it looks awkward compared to the rest of the graph. That is where wrong readings were given. And therefore, we can find the coordinates for that point there, for this point here, when we had wrong readings. Okay. And what are they? You look at the time axis. This is the time axis. This would be 0, 1, 2, 3, 4, then 5. That point is on T 4 seconds. So the coordinates here will be T and what? And mass in that way. So in terms of where T is, when we had incorrect, oh, I think I got it wrong here. It should be here, sorry. That should be 5 plus 1, so 6, 7, 8. So when the time is 6 seconds, so T6, we find the mass to be, let's see, this one is 3 here. So it is not exactly at 3. It is slightly above 3. So I can say 3.1 grams. So that is the coordinates. Remember, even in your mathematics, the XY coordinates. This is what we're talking about here. But here, your x-axis, it's your time axis. Your vertical axis, which is your y-axis in mathematics, it's your mass axis. So hence the coordinates here has to be time, mass. Right. Next, so we would have written that down here as T6 mass 3.1. 3.2.2, how long in minutes the reaction lasts. Here you read the graph. The reaction is happening from 0, it goes, but when the leveling happens, that point there, the graph is leveling up. That tells you that at that point, that is when the reaction basically stopped. So at what time was that? It was, this is in minutes, not seconds. So this will be 10 minutes, 11, 12. So at the time, 12 minutes, that's when the reaction stopped. Okay, the reaction took 12 minutes. Right. Next, how long in minutes it takes 75%, which is 3/4 of the reaction to occur. You go back to the graph. Now, 75%, 3/4. If you look at this mass here, the total mass that reacted is 4 grams. So what is 75% of 4 grams? 75% of 4 grams is 3. So you can, if you are not so sure, you can say 75 over 100 of 4. What will that be? You work that out, you will get it to be 3, because anyway, 4 to itself, to 100, it will go 25 times. 75 divided by 25, that gives you 3. So your 75% is at 3, all right? So if you are to find, okay, how long in time did it take for the reaction to have 75% of its content having reacted, it means you will say, hey, okay, this is the point we're talking about. At time, when the mass is 3 grams, at that point there, and how many minutes were there? Is 1, 2, 3, 4. That is 5. So at time 4 minutes, that's when 75% had reacted. Okay. There we go. Next, pushing still on question number 3, coming to this question here. The experiment now is repeated using hydrochloric acid of a higher concentration. It is found that the rate of the reaction increases. Use the collision theory to explain this. Now, when you increase the concentration, you are increasing the number of moles. So number of moles had increased, okay, leading into more collisions, and of course more effective collisions, all right? And then if you have got more effective collisions, it means you are actually producing more of the results or the products that you are actually forming, because you've got more of these things now interacting, rather than when they are less concentrated. One comes, a collision happens after a long time. So you have got more effective collisions happening per unit time, okay? Per unit time. And that is the collision theory. How would a higher concentration of hydrochloric acid affect the following? Okay? We only write increases, decreases, or remains the same. Loss in mass per unit time. That is going to increase, of course. All right? Next, 3.4.2, total loss in mass. This is going to stay the same. It's going to stay the same because you can only produce 4 grams here. But how fast you get to the 4 grams will be different in terms of when you're using a dilute hydrochloric acid and when you're using concentrated hydrochloric acid. The time for the reaction to reach completion, obviously you're going to take a shorter time this time, given that you're using a concentrated acid. So the time to get to completion, the 12 minutes, will now become less. It won't be 12 minutes anymore. It will be less than 12 minutes. Okay. Right. Now, lastly, or part of the last of this question here, apart from concentration and temperature changes, write down 2 other changes you can make to this reaction here to make it to take place faster, so to increase the rate of the reaction. 1, you can introduce a relevant catalyst to do that. Or if you check from the information that is given to you, because we can't talk temperature or concentration, you would see that you're given calcium carbonate in lumps. So you can crush it into powder, okay? Crush calcium carbonate into powder. And what are you doing when you do this? You are increasing. So you can actually write this. You can increasing the surface area of this reactant so that it can react faster. Now, calculate the mass of calcium carbonate used when the reaction is completed. Assume that all the gas that was formed escaped from the flask. Now, what we know about carbon dioxide that was formed, it's 4 grams. And from the 4 grams, we can know how many number of moles of carbon dioxide have been formed. And from there, how do we get it? You can go to your periodic table here and say for carbon dioxide, what is the molar mass of carbon dioxide? For carbon, there you've got 12. For oxygen, you've got 16. So you can come back here. You can come back here and say, all right, this will be equal to 4 grams divided by the molar mass of carbon dioxide will be 12 plus 2 into 16. That will be 4 divided by 44, and that should give you, okay, let's just do that, and then we take some break. So this is going to be 4 divided by 44, and what do we get? We're getting 0.09 moles. Okay, so that is 0.09 moles. 0.09 moles of carbon dioxide that has been formed. And from here, then we can work out how much mass of the calcium carbonate that has been used. Let's take a break.
Thanks, TK. Okay, guys, I'm going to look at your questions. I can see you guys are asking me all kinds of questions, so I'll take a look at them at the break, discuss them with TK, and hopefully I can give you the answers. But thank you, Maureen and Irene, our favorite twins, for tuning in here at Mindset. We will see you guys after the break. Welcome back, guys. So you guys are ready, you guys are excited, you are tuned into chemistry or physical sciences paper 2, because me and TK are ready to give you some equilibrium questions, and you guys have been asking for them, so now your time to shine has arrived. So TK, please, let's get going with those.
Thank you, Megan. And now, just to round off this one, and then we move on to that equilibrium question. What I did here is, remember here we're calculating for the number of moles of carbon dioxide that have been formed. Okay? From this here, we were able to see how to calculate for the number of moles. So here we know that 0.09 moles of carbon dioxide have been formed. Now, during the break, I also wrote this equation down here as well, because there's something I need to show you here. Now, if one, according to this balanced chemical equation here, 2 moles of hydrogen will give me 1 mole of carbon. Now, if I have 0.09 moles here, the number of hydrogen chloride moles that I would need will always be twice that one. But what I am asked to do, it's actually to find the mass of calcium carbonate that has been used. So I will go to calcium carbonate and say, according to this ratio, 1:1. So if I produced 0.09 moles of carbon dioxide, I must have used 0.09 moles of calcium carbonate. So I will say here that calcium carbonate moles would be equal to 1 times the carbon dioxide moles, okay? And that would mean 1 times 0.09, and therefore I also have 0.09 moles of calcium carbonate that has been formed. Now the question wants me to find the mass of calcium carbonate formed, okay? So what I want is the mass there. How am I going to get it? I'm going to say, from this equation that says number of moles is found by given mass divided by the molar mass, the mass will be equal to number of moles times the molar mass, and this time molar mass of what? calcium carbonate, because that is what I want to find out. So this will be 0.09 times what is the molar mass of calcium carbonate. You go back to your periodic table. It is given to you at the end. For calcium, I've got 40. For carbon, already I've used it. I've got 12. And for oxygen, I also have used it. I've got 16 there. So I can work out the molar mass there. So that will be 40 plus 12 plus 3 into 16 for oxygen. And I can work that out quickly. All right? So that actually, without waste of time, 0.09 times, this will work out to 100, okay, grams per mole. You multiply 0.09 by 100, you would see that 9 grams of calcium carbonate would have been used for you to get 4 grams of oxygen used up. Okay, now let's move on to this question here, question number 5, right? It's an equilibrium question. So sit, listen, take your notes, and learn. A hypothetical reaction is represented by the following balanced chemical equation below. A plus B giving us C. These substances are all gases. It's hypothetical. In other words, these are not real elements. These are not real substances. It's just something that we think of as hypothetical. And this has reached a state of chemical equilibrium. And we want to zoom straight to calculating the Kc here. Initially, you've got 3 moles of A and 6 moles of B that are mixed in a 5 cubic decimeter container. When the reaction reaches equilibrium at 25 degrees, it is found that 4 moles of B is present. The equilibrium concentration of C is 0.4 moles. Okay? Now, this question was part of a section of other questions, so I need to read the bottom part here. So an equilibrium is reached with those information that we were given there. Let's see what this second part of the question says. In a second experiment, the initial number of moles of B, remember initial with B you had 6 moles. Now that initial number of moles of B is now increased while the initial number of moles of A and the temperature remains constant. It doesn't change. So for A we still have 3 moles. But for B there is something added, maybe X moles there, because we are not told. Now calculate the number of moles of B that must be added to the original amount so that the concentration of C at equilibrium is 0.8 moles per cubic decimeter. The equilibrium constant is given to us as being 0.625. Okay, and you are working for 9 marks here. Now, the key starting point there will be the concentration of C, which is given to us, as 0.8 moles per cubic decimeter. And from here, I can work out the number of moles at equilibrium of C, because this is the equilibrium concentration of C. Number of moles from concentration, okay, number of moles, I think if you remember what you have done, if you calculate for concentration, concentration is given by number of moles over volume. Okay? Now, if I want the number of moles, that will be equal to concentration times volume. So for C here, the concentration is 0.8 times the volume is what? It's 5 cubic decimeters. And what are you going to get there? All right? So you use this, say 0.8 times 5. And what do you get? You get it to be 4. Okay? So you get the number of moles of C to be 4. So you've got 4 moles here of C at equilibrium. I'm doing this because I want to use moles in my table here, and I'm going to set it up now. Okay, now let me see here what line I can use here. Let me use this one here. All right, so if I have my lines like this, okay, want to have ratio initial change, and then I would have equilibrium moles, then I would have equilibrium concentrations. Okay, right. So if I have that, I will do this now. But don't me for all this. That line there. I have that, and I have that. Okay, then come back to my writing here. So this is A, this is B, that is C. And I want to write the ratio in which these are combining to give me the product. From the equation here, you can see that 1 mole of that combines with 2 moles of that to give me 2 moles of that. So it's 1:2:2. That is the ratio. So 1:2:2. Now, this is the law. This is the rule, if you like. You are going to follow this. Now, we are told that at the beginning, initially, so you can write initially here, with A, remember, we were told we had 3 moles. But for B, we had 6 that was added, and something was added to it. We don't know what was added. We want to know how much of B was added. We can just say, let's say the number of moles of B all together, it's X. Then we have X there at the beginning, and there we had nothing. All right? Then we move on. Would have to prolong my lines a bit here. Sorry about that. So we have all the sections that we need. Okay? All right. So coming to the other part. For me to fill up the other part here, like the change, I need to start with what has been given to me. Here it will be equilibrium moles, and here it will be equilibrium concentrations. All right? And I'm told that equilibrium moles, from what I've calculated for C here, I found that to be 4 moles. So equilibrium moles for C is 4. And the concentration of C is 0.8. That is given to me. And from here, I can work out everything else backwards using the molar ratio. Okay? Now, if 4 moles of C has been formed, it means I can say there the change was +4 to whatever we started with for C. But for here, if I had 4 moles formed for C, how many moles of B must have been used? 4 moles must have been used, because according to the ratio, 2:2. So 4 moles must have been used here. So this will be -4 for B. So down here, according to the ratio, if I have 4 moles here, if I have 2 moles of C, I would have used 1 of A. So 1 is always half of what is formed for C. If C that is formed is 4 moles, half of that will be what has been used for A. So 2 has been used. So I'll write -2 there. Coming down to the next line, I will then say, okay, this line, equilibrium moles, would mean that for A, it will be 3 minus 2 here, it will be 1. For B, it will be X minus 4. I don't know what X is yet. I want to find out what it is. Then I can work out the equilibrium concentrations here. Because the volume is 5 cubic decimeters. So if I've got 1 here, this will be 1 over 5. That will be 0.2 cubic decimeters. So the units here, of course, are in cubic decimeters. So 0.2 there. This time, x minus 4 over 5. I don't know what x is, so I still have to work it out. Okay? And the other concentration, of course, has been worked out for me. So from here, I can then find the Kc. The first thing here is for me to write down the Kc expression correctly from the given equation. So this will be the concentration of what? If you look here, all these substances are gases. So they are all going to appear on my Kc expression, all right? But then B is 2, C is 2, so this will be to the power 2 to the power 2, A will be to the power 1, all right? So I would have my Kc expression as C, concentration of C squared, divided by the concentration of A to the power 1, times the concentration of B to the power 2. Once I've done this, then I substitute into it. I am given in my question that Kc for this reaction is 0.625. I will confirm that quickly. It's 0.625. So let me confirm that. Yes, 0.625. So that's the correct value. So it means on Kc, I'll substitute it with 0.625. And remember, this is marks that you are earning. By writing that correctly, it's a mark already. Substituting correctly to this Kc, it's a mark already. Equals concentration of C. Now from the table, concentration of C is 0.8. So 0.8 all squared divided by the concentration of A. We found it to be what? 0.2. So this will be 0.2 to the power 1 times the concentration of B. Concentration of B is x minus 4 divided by 5, and therefore I will put it as is here. X minus 4 divided by 5. All squared, of course. And that line goes further like that. Okay? And when you work this out, you will find that x works out to be 15,3. And that, if that works out to be 15,3, all right, this is the total number of moles of B. So B equals to X moles equal to that. But then the added moles of B added will be equal to 15.3 minus 6. And therefore, that will be 9.3 moles. Okay, so that is how you could work out that equilibrium question there. I hope you were able to see how you start with what is given at the equilibrium, and you can work backwards and find the number of moles of the other things. All right, so I tried to plug in values there because I tried to work it out earlier on without just doing it, taking more time. We have very little time to try and round off here. I want us from here to go back or to proceed to this question here with the remaining time that we have. Now this question here, question 6, talks about electroplating. Somebody, I understand, asked about electrolytes or electrolytic cells and other things. This is an electrolytic cell, all right? It is, and here it's used for electroplating. All right. And this cell here converts electrical energy, which is that, to mechanical energy, which happens inside there. All right. 6.1. Write down the energy conversion here. Electrical energy to chemical energy. Electrical energy to chemical energy. Because this is an electrolytic cell. This is what it does. If it was a galvanic cell, contrary to this one, the galvanic cell will be converting chemical energy into electrical energy. But for now, we're dealing with an electrolytic cell here. 6.2, direct current is used in this process here of electroplating. Give a reason why alternating current is not suitable for this job. It is not suitable because as it's an alternating current, it changes the polarity of your electrodes. The polarity of the electrodes must not change during electroplating, and that's the reason why it is not used. So polarity of the electrodes must not change, must not be changed during electroplating. You don't do that, and therefore AC cannot be used. Okay. 6.3, which type of reaction, oxidation or reduction, takes place at the spoons? Now, these spoons are made of iron, and they are to be made silver, okay, for protection, to improve the way they look and everything else. So what is the type of reaction that is happening there? It must be reduction, because we are reducing the silver ions, Ag pluses, to get them to be silver that will be coated around that spoon. Okay, so that's what's happening there. I don't have much time remaining here, so this should actually suffice as what we could do here up to this point. And if I am to just answer just that one there, electrode Y, if I were to write down what is happening there, you've got silver oxidized into silver plus by losing that electron there. So that is the oxidation happening on the silver electrode. So Y is the silver electrode.
Thanks, TK. Good luck. Good luck, Matrix, for tomorrow. The winner of the Curio Challenge is Tanae. We'll post it on the page for you just in case I spelled it wrong. But good luck from me and TK, and we'll see you again soon. Cheers.
Good luck indeed.